Number 1. From test 2, we saw that linear regression does not fit the fiddler-crab data well. A polynomial of best fit approximated the data the best, using a polynomial of degree 5. The description from test 2 was, this data set are the results from an experiment conducted in the spring 2010 at Sacred Heart University in a biology lab. This data describes the mean weight change in grams for fiddler crabs over the course of 100 minutes. When the fiddler crabs were submerged in a saline solution as an experiment of osmoregulation. Let us first design a line of best fit for this data, and then we want to know what that least squares line of best fit is. So, for us to do this, we first need the data, which I have open, not there, here we are. This lovely data set. And in order for us to do this, we need to go to data on here, and after you put in that analysis tool pack, this data analysis box should be available. You'd click that and hit on this regression analysis tool, and then hit OK. Now we need to select our data. The y values come first, which is this mean change of weight in grams, and we need the x values after that, which will be this time. I'm going to leave this checkbox here for labels, since we have the labels in the first row. And this is going to put this information into a new worksheet, and I'll keep all of these checked off, and then hit OK. And I apparently clicked the wrong number of values. Yes, I did. How did that happen? Okay. The x values are just from A1 down to A7. Okay. Now it worked. This will give us all of this lovely stuff in 3 graphs that are kind of on top of each other. Let me just take a few seconds to move those. Okay. To answer the first portion of that prompt, we had wanted the line of best fit. That would be these 2 entries. Okay. The intercept, that would be our value for A in our linear relationship, so 0.4286, and the coefficient for the slope is 0.0094. Okay, so let me write that into our equation here before we do this hypothesis test. So this will be y hat is equal to, that was 0.4286 for the intercept, and then the slope was 0.0094x. Alright, and x was that time in this case in minutes. And y was that mean weight change. Mean weight change. And that was in grams. And now we want to run a hypothesis test from that data. So the hypothesis test for this, which is going to be based on these 2 numbers, but the slope for the hypothesis test, you're saying the null hypothesis is that the slope, so beta, is equal to 0. Or if we wanted to write that in words, that there's no association, no linear relationship. No association. The alternative is that there is a linear relationship. So beta is not 0. And based upon this test, we have a t-stat of 2.50 and a p-value of 0.0666. Alright, so let me put that on here. So the t-statistic for this had been 2.50 and the p-value 0.0666. Alright, and let's now analyze this with an alpha of 5%. That would be something that you would need to specify before running it, but I failed to write that on this. We could see this p-value is indeed above this level of significance. So because it is above the level of significance, right, that means that we do not reject this null hypothesis. And you might be wondering to yourself, well, how can we determine that based just upon that, since we have all those assumptions that we need, like it being a simple random sample. That was not specifically identified with regards to this. However, though, naturally, choosing the fiddler crabs that were indeed used, that would have been a randomized experiment in and of itself. But looking at these different plots that we have, the normal probability plot down here, this shows a clear pattern, kind of almost like an x cubed pattern, since it goes up, levels off, and then kind of goes up again at the end. So this is not in a straight line. It needs to be a straight line for it to be normal. We could see from the timeline fit plot, these orange boxes, those are the values of the values of the line at each of those points. You can see they are way off from all those blue dots, especially this at the beginning, right? And also this residual plot kind of shows almost like a quadratic type of residual, right? We can even change this to a histogram. I right-clicked it and then hit change type, and then we hit statistical and histogram. I'm just going to change this bin width very quickly to, this uses 2, let's go up to 5. That definitely does not look normal. If we keep increasing it, it will look less and less and less like a normal distribution. So this is not normal at all. It looks more like a skewed left distribution, if anything. But regardless, it's definitely not normal. Let me put this back onto that scatter plot. Before continue, not that one, this one. So that did not show. That shows kind of a quadratic based relationship. So we could see from just those 3 graphs by itself, it's definitely not appropriate to even be running this test, since it fails these assumptions. But also that p-value also shows that it's definitely not linear. So, because of that, the conclusion or interpretation that we can make of this would be, and let me actually type that on there so it's that much easier to see with regards to this data. Do that down here. Down here. At the 5% level of significance, we, now since the p-value is indeed 0.0666, that being greater than a level of significance, that means we are not rejecting this null hypothesis. So we do not have sufficient evidence to reject the null hypothesis. which is just fancy schmancy talk for the idea that this then means there's no association. Well, I should probably specify no linear association, since this was for linear regression after all. So there's no linear association with regards to this particular data set.